Okay. So far, you've learned about how to add vectors and multiply a vector by a scalar. Okay. And there are other operations defined for vectors, and one is called the dot product. Okay. Now, what is the dot product? All right, let me go down here a little bit in the ebook. Okay, this is the definition of the dot product between two vectors. If you have, and notice that in the definition here, A and B are in bold letters. That means those are vectors. And then there's a dot between them. The dot product between two vectors is defined as the length of vector A times the length of vector B times the cosine of the angle between the vectors. Now you might, and by the way, theta is between 0 and pi, between 0 degrees and 180 degrees. Okay, so you might wonder, well, why do they come up with this operation? Well, let me show you here. Go up a little bit. Okay. How many recall that the definition of work is force times distance? If you do work on an object, okay, if you're able to move the object and the object moves some distance and you applied a force to the object that moved the object some distance, that's called work. How many recall seeing that maybe in middle school or high school? Okay, IB recalls that. Yeva, Narina, and Brian, absolutely. Matthew, yes, yes. So let's take a look at a situation, but usually, like that definition of work equals force times distance, is for when you push an object or pull an object on some kind of horizontal platform. But you can have a situation like they have here in Figure 1, where you have an object at point P, and the object moves a certain distance. So you move the object from point P to, well, say to point S. All right, but the force you're applying the object at it's not a horizontal force. It's a force that's at an angle theta to the object. So it's like if you're pulling a wagon, the handle of a wagon. Okay, think of like the wagon at point P, and the handle of the wagon is that blue vector, line segment PR. That's the handle of the wagon, and you're pulling the handle, and the force, that's the force vector. Okay, so the force vector has horizontal and vertical components to it, right? The force vector has a horizontal component and it has a vertical component. Well, I want to say it's the right way. The portion of the force that does the work is the horizontal component of the force. Okay, and that horizontal component of the force is equal to the magnitude of the force times the cosine of theta. Because if you notice in the picture in Figure 1, there's a right triangle formed by points P, R, and S, right? P, R, and S is a right triangle. The cosine of theta would be equal to the length of that leg, PS, divided by the length of the vector f. So therefore, the length of PS, okay, that ray is equal to the magnitude of the force times the cosine of theta. And so therefore, the work then done, let me see if I can make this there. The work done in moving the object from point P to point S using the force vector at that angle is equal to the length of, I want to say this the right way. If you were to have that object go from point P to point Q, which is the entire distance in the direction of the d vector, the work by Formula 1 would equal, work is force times distance always. Work is force times distance. The distance is the length of the vector d, and the force that is used in moving the object in that direction is equal to the magnitude of the force times the cosine of theta. So work is equal to the magnitude of the force times the magnitude of the distance or length of the distance vector. Well, let me say that another way. The work is equal to the magnitude of the force vector times the magnitude of the distance vector times the cosine of theta, and theta is the angle between those two vectors. And that's how we come up with this definition of the dot product. It comes up through the idea of work. Okay, does that make good sense? Okay, Simon's comfortable, Angela's comfortable, Yeva's comfortable. Okay, are there, R's comfortable? Excellent, Marina's comfortable. Are there any questions so far? Okay, great. Okay, well let's do an example here then. Let's do an example. Hold on, I guess I have to. Thought I had this, but I guess I don't. Hold on. Let me just put this in. One moment, I just have to upload a document. I thought I had it uploaded. Give me a moment here. So I'd like to do an example with you. Now remember, if your force is in pounds, okay, what would the distance have to be in terms of units? If your force is given in pounds, then what distance would we use? Feet, that's right. So you would get foot pounds. Okay, and so work can either be in foot pounds, or if you're applying a force in terms of newtons, then distance has to be measured in what? If you're applying a force with newtons, distance has to be measured in meters. That's right. And then work is going to be Newton meters or joules. Okay, so let's do an example here. Okay, let me give you a moment to copy this example down, and then we'll work through it. Yes, Simon. Simon has a question, I believe, or at least. Okay, no problem. No problem. All right. So I have a nice picture. Don't worry. Don't worry. So uh, let's take a look at this. So in this problem, we have a crate that's hauled 8 meters up a ramp under a constant force of 200 newtons applied at an angle of 25 degrees to the ramp. We want to find the work done. So these kind of problems, well, what can be very helpful to do these kind of problems? What can be very helpful?
A diagram or a free body diagram?
That's right, Ara. That's right, IB, Ava, and Alberto. That's right. So, okay, let's get a diagram. Here's a diagram. So, okay, what we have here is the crate, and the crate is right here. This is the crate. And I just have a ramp. I just drew a picture of a ramp. The crate is moving along the ramp. Okay, the crate is moving along the ramp. Try to draw, trying to avoid using that, well, maybe I can try using it, all right. I just gotta be careful about the buttons I touch. Hold on here. Okay, so we're moving the crate along the ramp, and we have our force vector being applied at an angle of 25 degrees to the ramp. So there's the force vector. I get it. And we want to find the work done in hauling this object 8 meters up the ramp. So the distance vector is there. Right, there it is. So we have a right triangle here, right? We have a right triangle. And the cosine of 20 degrees would equal this distance x over the length of, over the hypotenuse, right? Because cosine is defined, the cosine of an angle is defined as the adjacent side of the right triangle over the hypotenuse. So this is true, and this means x is equal to the length of, or the magnitude of the force times the cosine of 25 degrees. Okay, so you take that and multiply it by the length that you're moving the object. And that's going to get you, and that's your dot product. So this kind of problem, it's one of these kind of problems where it just helps so much to just draw a picture, because it just, you know, it just kind of helps you keep things organized in your mind, and it's well worth the time to do. So that's going to be 1,450 joules then. Please let me know if you have any questions. Okay, so a lot of these things like the dot product, like the dot product, cross product, which we'll learn at section 9.4, that these come from needed applications, particularly in physics. Okay. Now the thing is, the way we have the dot product defined so far is that the dot product of two vectors is equal to the product of the length of those vectors times the cosine of the angle between them and between the vectors. But you see, you could be given two vectors. Okay, you could be given two vectors, and you might know the components of the vectors, but the angle theta, you might not know the angle theta. Now, it doesn't mean you couldn't find theta, but it would be nice if we had a formula to compute the dot product based off of components. And we have that. We have that. So let me go a little bit more into the book here now. Let's keep moving through this section. By the way, before I get there, let me mention, it says two vectors are orthogonal. Orthogonal means perpendicular. Two vectors are orthogonal if and only if their dot product equals 0. Why would that be? So if you have, good, that's right, that's right. If you have, I mean, if you think about the dot product, A dot B, notice I'm putting my vector symbols above there. Okay. Now, in order for A dot B to equal 0, right, if A dot B equals 0, well, that means either the length of A is 0 or the length of the vector B is 0. But that's not very interesting, right? I mean, when's that going to happen? But the third option is the cosine of theta equals 0. Well, if the cosine of theta is equal to 0, just that's a 0, right? Then this means then that theta would have to equal 90 degrees, right? Because the cosine of pi over 2, or 90 degrees, is 0. And that's why anytime you have two orthogonal vectors, A and B, the dot product equals 0. Okay? All right. All right, let's get back to the look here. So we want a way to compute the dot product if we're just given components. And they go through a little proof here, and they show, hold on here. Hold on, do I have, let me see. That isn't showing right. Let me go back here. One moment, everybody. Let me see what's going on here. Yeah, okay. Okay. They use actually the law of cosines to prove that if you want to find the dot product between two vectors, and in this case, they have vectors that are in three-dimensional space, but it would also apply for two-dimensional space. You can compute the dot product using this definition. You can compute the dot product that way. Okay, and it's very nice. It's a very nice, handy definition. It's actually, it's a result that they prove. Okay, so A dot B is equal to the product of the A1, B1 components plus the product of the A2, B2 components plus the product of the A3, B3 components. And this is very handy, for instance, if you wanted to find the angle between two vectors. There, by the way, is the formula when you're in two-dimensional space. So, I mean, it's no big deal computing dot products. It's no big deal computing dot products. They show that in example 3. I mean, if there's anything unusual about those 3 little examples, just, let me know. But hopefully, hopefully this makes good sense. Okay, are there any questions on that? Gave us good, okay. Okay, well let's move on. Let's move on then. So sometimes you want to find the angle between two vectors. How would you do that? Well, in this case, you have vectors with components. Vector A has components 2, 2, -1. Vector B has components 5, -3, 2. Okay, what would the angle be between those two vectors? Okay, how are we going to find that? Well, what you can do is this. You certainly can find the length of each of those vectors. And the dot product between A and B turns out to equal 2. But the other definition of the dot product, where A dot B is the length of A times the length of B times the cosine of the angle between the vectors, that means the cosine of the angle is equal, hold on, that means the cosine of the angle is equal to the dot product divided by the product of the lengths of the vectors. See, so you get cosine of theta equals 2 over 3 root 38. And what would you do now? To find theta, what do you have to do to find theta? If you have the cosine of theta is equal to 2 over 3 root 38, how would you find the angle theta? If the cosine of theta were equal to pi over, if the cosine of theta were equal to root 2 divided by 2, well, you know theta would equal 45 degrees, right? Theta would equal pi over 4. But in this case, cosine of theta equals 2 divided by 3 times root 38. That's not a nice number. That's right, Yeva. That's right, Alan. Use the arc cosine. Use the arc cosine. So theta would then equal the arc cosine, and you get 1.46. Now that's radian measure, but in degrees, you would get 84 degrees. So you all know, right, if you have, if your theta, let me just clear this, yep. If theta is 1.46 radians, if you want that in degrees, okay, how many degrees are in pi radians? You remember? I mean, you should remember, right? That's right, good. 180 degrees. Good, Yeva. And so if we work that out, now, of course, the radians simplify out, and we're left with degrees. And if you take 1.46 times 180 and divide it by pi, you're going to get 83.65 degrees. And of course, that angle is, let me just see here. The angle would have to be a positive angle, right? Because if the cosine of theta is positive, then we're talking an angle between 0 and 90 degrees. Remember, we're restricting theta to be between 0 and 80 degrees, 0 and 180 degrees. So theta would have to be an angle less than 90 degrees. Now, if the cosine of theta were a negative number, then that angle would have to be somewhere between 90 degrees and 180 degrees. Right? So, okay, good stuff here. Good stuff. Let's keep rolling here. Let's keep rolling. So, book has good examples. I'm hitting on just, selected things. So properties of the dot product, these are all properties. Okay, these are all properties of the dot product. And property 4 says that if that's a property that comes up a lot. If you have a scalar times a vector A and you dot it with the vector B, the scalar can be moved outside the dot product. Okay, that's kind of a handy property. Okay. Any questions so far? Okay. Let's keep going. Let's keep going. All right. So another thing that dot products are helpful with are projections. Now, projections are covered a lot in linear algebra. That's Math 284 at Montgomery College. But of course, they're important in physics as well. So what is a projection? Well, if you look here at figure 5, you have pictures of projections. So the first picture is the projection of the vector B onto the vector A. So if you were to take the vector B and collapse that vector down onto the line segment defined by the passing through P and if you consider the line passing through points P and Q, and you take the vector A and project that, take the vector B and project that down onto that. Well, let me say it again. In the picture, they have a vector B and a vector A. If you project the vector B onto the vector A, that's going to give you that red vector. with beginning point P and ending point S. The vector PS is the projection of the vector B onto the vector A. Similarly, in the second picture, if the vector B is going that direction and you project that down onto the vector A, you're going to get that projection. So we are interested in finding, in being able to find what these projection vectors are. Okay, but of course, we recognize again that we have a right triangle here. We have a right triangle, and so I noticed, by the way, in the ebook they have like you can explore vector projections. So there's some interactive materials in the ebook. Feel free to look at those. But now here in this picture, you have what they call a scalar projection. So in other words, if you project a vector B onto the vector A, that projection vector is some multiple of the vector A, because the projection vector is parallel. The projection vector is on the vector A, so it's parallel to the vector A. So the projection vector is a scalar multiple of the vector A, and that scalar multiple is your component. It's your scalar projection of the vector B onto A, or the component of B onto A. And we need to find what those are. So how do we find these? How do we find these things? How do we find them? Well, first of all, they note, of course, the definition of the dot product. And I guess if you look in the figure above here, figure 6, they note that the scalar multiple of the vector A that gives you the projection vector would have to be the length of the vector B times the cosine of theta. Because again, the cosine of theta equals the length of that red vector, the adjacent vector, divided by the length of the vector B. So that means then that the length of the red vector would equal the vector, hold on, let me just write it on my, hold on. I don't like to, I mean, I have it, I'm comfortable, but I just want to write it down so I say it the right way. Yeah, so the projection vector is the vector PS, and we want we want the length of that vector PS. Since the cosine of theta is equal to the length of the adjacent vector PS divided by the hypotenuse vector B, that means the length of PS is equal to the cosine of theta times the vector B. Okay, and that is your component vector. Okay, so whatever that number is, that's the projection vector is going to equal the multiple that scalar times the vector A. So what they do is they say, okay, how can we compute that component? Okay, well, take that scalar projection. If you take, if you remember, the dot product of A and B is the length of A times the length of B times the cosine of theta. So then B, the length of B times the cosine of theta, which is our scalar projection, is simply equal to the dot product of A, B divided by the length of A. Okay, that's what that is. But let me just see here, one moment. But you can write that as, they have a typo here. There should be in that A in the bottom, that vector A in the bottom, there should be a length there. Okay, so what I'm saying is there's a typo in this equation here. They should have the last step there, that vector A in the bottom should have absolute value around it, absolute value signs, because it's the length of A. But this then shows that, take this off. Yeah, this shows then that how they get the scalar projection of B onto A. But now if you want the vector itself, the vector projection, you're just going to take that, that scalar projection and multiply it by the vector A, but it's normalized, the vector A divided by the length of A. Okay, so I might have misstated that a little bit earlier. Writing the vector A divided by the length of A ensures that you have a unit vector in the direction of the vector A. You just multiply it. So let me see here. I can maybe make this a little more clear on the whiteboard. Okay, so the projection of the vector B onto A, okay, is equal to A dot B over the length of A times the unit vector going in the A direction, in the direction of A. Okay, I shouldn't have a dot here. This is times, actually, not a dot. When we write dot, we think dot product, right? We got to be careful. See? So basically, this is a multiple of a unit vector in the direction of the vector A. That's what you have. And if you look at the picture, if you go to figure 6, okay, just go back here for a moment. Yeah. If you look at figure 6 here, come on, get that off. Hold on. That off. You have to forgive me. I don't know why it keeps going blue there. But we won't worry about it, okay? The picture there, the projection vector, the red vector, it's a multiple of, I want to say it the right, it's a vector that goes in the direction of A. And so take the vector A, normalize it so it has length 1, and multiply that normalized unit vector by that scalar projection, and that gets you your projection vector. That's how it works. That's how it works. And if you ever take linear algebra, you'll find linear algebra deals with projections in a little more general sense. But certainly for 2- and 3-dimensional vectors, you could use what you learn in linear algebra and rewrite it as you see here. Here we want to have like some handy like formulas. And so we have them. So I'll tell you what, let's do an example. I'd like to do an example here before we go on break. So let me go, let's see here. Okay, let me give you a moment to copy this example down. Now this example is a Dr. Duty example. Okay, it's not in the textbook, but I think it's a very nice example for you. Okay, please let me know if you have any questions. You want to find the projection of this vector B onto this vector A. Okay, so find the projection of the vector B equals 5i onto the vector A equals 3i minus 4j. What would be helpful for this kind of problem to give us an intuitive feel? What would be really, really helpful? A drawing, absolutely, Sadhana, I agree. So I have that on the next page. Okay. Notice I used a ruler for this picture. You know, I think it's a good idea to, you know, how many maybe haven't used a ruler or a protractor in a while? Might be good to take it out of your desk. All right, so here's this vector B. Okay, there's the vector B. And we want to project that onto the vector A. The vector A has components 3, -4. So there's the vector A. And you can see I tried to draw it pretty accurately. Whoops. That in red. And the projection vector, let's see, maybe I'll put that in green. There it is. Okay, so this information that I have off to the side here is basically information we talked about. course, I'd have to, this is the x-axis here. Let me just, I don't want to write over that, right? X-axis. So the scalar projection, using what we learned, the scalar projection and is that reasonable based on the picture? In other words, if we look at this green projection vector, okay, if we look at it, and if we were to take a guess at how long the vector is, given the scale that we have, it's not perfect, but I'd say it's about 3, a distance of 3. Wouldn't you, roughly? Roughly a distance of 3. If we were to, take that vector and sort of rotate it into the y-axis there, you'd see it have a distance of about 3, and so it is reasonable based on the picture. Are there any questions so far? Okay. Marina's good. All right. Good, Yeva. Good, Alberto. So, okay, now what we want to do is find out what the projection vector is. Well, the projection vector goes in the direction of the vector A. So all we need to do is take this value, this scalar projection of 3, and multiply it by a unit vector in the direction of A. And that's what we have on the next page. The vector projection of the vector B onto A is simply equal to 3 times this unit vector in the direction of A. I mean, when you think about it, it's really quite simple. I don't want to say simple, but it makes sense. Let's put it that way. And the reason I'm sort of emphasizing, in this example, I'm emphasizing the geometry of the problem because I think it helps to understand. I think understanding projection vectors and the definitions are I think it's helpful when you have the geometric feel for the situation. And it turns out that this projection vector is going to equal 9/12 and -12/5. Now, 9/5 is 1.8, 1.8. And negative 12/5 is negative 2.2. And if you look at the picture, if you refer to the picture, and look at that green projection vector that's drawn on the picture, you know, that's pretty darn good. Let me just go back here. I'll let you copy this, but if you go back here, okay, and if you focus on this point here, that point looks to have coordinates about 1.8 and negative 2.2. You know, the tip of the projection vector. That's pretty good. It's pretty good. That's why I like to use rulers when I draw pictures, because it helps me. It just helps. It helps. It helps. Why not? You know. Are there any questions at all on this example? All right, Ye was feeling good. Simon's good. Narina's good. Excellent. Okay, well, then I will go ahead and stop the recording here. Excellent.